Hello everyone. So today we are going to do this question word ladder 2. So earlier I have made video about the word ladder 1 and it is pretty much interesting question in which BFS is being used and we are required to make words by just the one difference and create a complete ladder out of it. But this question is the variation of that previous question which I was explaining till now. So now let us first raise this question. I'll explain you what's the difference between this one and how to come up with the approach. Like from the brute force manner to the most optimized manner which we can make. And then I'll give you the code walkthrough for the same. But before that, it's important to understand this question and even the approach of the question. So see, a transformation sequence from word begin word to word end word using a dictionary word list which is being provided by them is a sequence of words where begin word S1, S2 and then after that such that every adjacent pair differs by a single letter. Every S of I for I less greater than equal to 1 and less than equal to k is in the word list. Note that begin word does not need to be in word list. Sk equals to end word. So here it simply represents that we are required to form a ladder and in that ladder each word should differ by just one. That's what they want to say. Means if we are having cock for the starting, then it should go ahead with dog, means just one letter change, and then it should go ahead with do, just one letter change, and then it should go ahead with dot, just one letter change, that is T. And if our end word is simply caught, right, then this is one letter change. So from cock to caught we are able to reach this particular. This is what it want to say in this. Now comes the next part. Now it says that given two words, begin word and end word, and a dictionary word list, return all the shortest transformation sequences from begin word to end word. Basically, this is the main difference between this and the previous question. In previous question, we were required to just return the length or the shortest transformation sequence. But here we are required to return all the shortest transformation sequences or an empty list. This empty list would be in that case when end word is not present in our word list. And it says that if no such sequence exists, and that would be only that case when end word doesn't exist in our word list. Each sequence should be returned as a list of words, that is begin word, S1, S2 till Sk, where Sk simply represent the end word. And why it is represented by Sk? It simply want to say that that end word is already present in the same. So that's why it is represented by Sk. And now comes the part that how we'll know about the end word. So it would be given to us already. Means these are the three things which would be given to us. This begin word may or may not be present in this particular word list, so that we can already put into this word list by our own. But this end word, this should be mandatorily present in this particular word list. And if it is not present, then at that moment only we'll return empty string. So that is also one of the scenarios we need to take care while doing this particular question. So this was all about the explanation of this question, and let us also first see about the constraint so that it would become easy for us to do the approach. So here you can see that begin word length is 5. Why her length is being considered? The thing is that we are required to check that cog to caught. This thing here only one word difference should be there. Means if this is some word in that word list and this is the begin word, then while moving from this word to this particular word, means moving to first word to second word, we should keep in mind about the length. So that's why they are also giving us the constraint about that what is the maximum length that a particular begin word could attain. And this end word and begin word length both would be same only, and the word list length, that is number of words, would be at max 500. And then word list of I dot n equals to begin word dot length. That simply means that whatsoever begin word length would be there, each word in the word list that would be also having this equal length. So that would be also one of the scenario we can consider, that here we are not required to check for the length present in the word list for each word. So that's why it becomes much easier to, now we don't need to think about the length of the words. So now comes the next part, that begin word, end word, word list of 5 consists of lower case English letters. This is also another thing which makes question much more easier, that now we are just having one type of letters only, that is all lowercase English letters, not even the uppercase. And the begin word and end word, both of them are never equal. That is also one of the scenarios. Else we would be obliged to return a list that would be consisting of just one begin word only. And that is not what is expected here in the question. So that's why in the constraint we have mentioned that they would be never equal. And then all the words in the word list are unique. So this simply represents that by the question itself there is no looping in this particular word list, so you will never reach a word again. So that's the thing it want to represent. But now comes the part about these constraints, and I've explained that what all these constraints represent. Now come up the part that how we are required to solve this question. I just gave you the example of the quad when it is transformed to, say, now I'm taking a new sequence, cat, then hat, then it is say transformed to hot, and then it is transformed to dot, and say dot as the end word and this is the begin word. Then is this whole scenario how we are to come up with the reaching this particular, because there could be one more path also where it could be say the word is means only one required to be changed. So say the word is dog, and then it is directly linked to this particular only. So here you can see that there are two paths to reach this particular dot, right? And say there are two more words in the same, right? So both are of the same length only, means they are equal length and shortest sequence itself, right? So in this scenario, there are two paths which could be reached, and we are required to return both of these paths the way they are returning here. And there are two paths and they are returning both of them, and both of them are the shortest sequence only. So now let me show you that how we are required to think about it. So now here comes the nice way of solving this question. The way we were solving for word letter when, now we can think about the same in this word letter 2, but with little modifications. The modification would be only this thing, that earlier in word letter 1 we were just thinking about doing BFS on our words, but now in this question we are required to do BFS not only on the words but also on the parts also. So that's why here we are required to do in such a manner. Now let us see about this. The nice way of doing this question is by using backtracking. So what we will be doing is that we will starting from the begin word, then traverse all the existing words until we reach the end word. That is the thing which we will be doing in nice manner. Yeah. And when end word reach, then compare the path length, find all the paths with minimum path length. So this third point is the thing which makes this question different, and this is what we are required to return even. But there is some flaws in this approach. It is inefficient because as there could be huge number of paths between two vertices, and that's also true. Like it is not necessary that there are only two words which would be having difference of one character. There could be a lot of words which would be having difference of just one character between them. What I mean to say is that there could be like cot, then cot could be connected to cat also, and this cot could be connected to dot also, and then this cot could be connected to say let us take gas dot could be connected to hot also. Here just one characters are different, right? All are having just one character difference. So that's why what I am saying is that there could be any scenario in which this could be the case. So that's why there would be a lot of paths. And say the end word is cat, then let us have it as bat, and then bag, and then cab. And like this, some words are there, then it also represents this, but this particular doesn't need this particular word. Let's say this is the scenario. So we are not required this path, but we are required only these two paths, right? So say there are a lot of paths, not only this one, but there are a lot of paths which are there, which not even goes till this particular word, right? So in that scenario only, we are required to just think about an approach where we are just able to come up with this particular end word only, and we are not able to come up with all other paths, so that we are comparing least paths only, but only those paths we are able to figure out which are having the shortest path. So these are the two things which we are required to consider. So here, let me show you what I want to say is that we need to check for shortest path. That is for sure, which we are required in this question. And the number of paths required to achieve this shortest path. These are the only two things which we are required to do in this question. And this is what I was explaining in this particular example, that there could be a lot of paths, and we are not concerned with a lot of paths. We are just concerned with a shortest path, and it leads to our end word. That is our concern. And this is how we are required to think about this question. So let us take one more example to explain this scenario. See, we are given with this begin words, end word, and word list like this. So I just made a graph like this. And now comes the part that how we are required to think about this and how many paths we can find in this particular. We can clearly see that there are 1, and then there is 2, and there is 3. Basically 3 paths are there which connect red to tap. That is also a scenario in this. So now when we traverse from up to down and then again up, this is also one of the concern which we can see in this particular, when it becomes a undirected graph, in which it can also go like red, ted, tat, it reaches tap, it's alright. But it can also go like red, then ted, then text, then rex, like this also it can go. And if there is some more line here and it connects to here, then in that scenario it becomes one of the longest paths. So that's what I'm saying, that when we traverse from up to down and then again up, this increases our path length, right? So that's the thing which we need to avoid. Means first two things are that it should be a shortest path and it should be the path which reaches our end word. And the third scenario, now these are the required ones, but the third scenario, this is one of the flaw which we need to correct. So we need to think that now how we can eradicate this flaw. Just think about it. In this particular graph only, we are required to just tweak this graph in such a manner that we can get rid of this flaw. So the answer to this is that thus we are required to make a directed graph. So this is our next step towards our algorithm and modification of it as naive approach. Our first modification was that we just required a shortest path out of all paths, and we need to keep a check that we are at that particular shortest path with the end word which is being there. And now the another check is that we need to make a directed graph. And one more concern which comes up here is that the scene which was here, this could also result in cyclic formation. So that's why our graph should be directed and even acyclic in nature, so that longest paths are completely eradicated. So that's why there shouldn't be any cycle in as well. Thus we are required to make a directed acyclic graph. So this is the thing, that how we now came from a naive approach to some modified approach. Now let us see that what changes are there which we are required to do. Now here we formed a directed graph, and we can clearly see that there is one starting layer, then there is one another layer, then another layer, and then there is end layer. So these layers only make us understand that how we can avoid that particular duplication thing which is there and that long paths which are there, and thus how we can just directly go towards our destination without going into a loop into our graph. And this all could be attained by this sector, like for avoiding visiting the previous edge again, we'll mark it as visited. So this is something we'll do so that we don't visit our previous edge again, because when they are connected in the graph, then there are chances that we also go towards our previous nodes also. So that's why when we do any graph question, in that we always maintain a visited node so that we don't do duplicate visits. But that is the scenario here. And then there won't be any edge between the words that are on same level. That also is the thing which we are required to take care. Because if there is some edge between TED to REX, right, if that is the scenario, means in any case, if we got a word which is just one word change from this TED, from this red, right, and then we got that word here, and then there comes a edge between the same, then in that scenario we need to avoid that thing also. So that's why we should always keep this particular thing in mind, that there won't be any edge between the words that are on same level. Thus iterating over any edge will bring us one step more closer to end word, and thus eradicates the work of comparing length of the path. So when we take this particular case also into consideration, that there is no edge between any node at the same layer, then we are able to figure out with our shortest path, and in that case no cycles would be there, and there won't be anything like that we are going towards down then up and then down, means no lengthening of the path. So that's why we are easily able to get our shortest path. Means in this manner we are required to make our graph. Now here what I have explained here is that what I would be doing here is, means now out of all this I am just required that how our functions would be made. So before explaining you this, that how our functions are required to be made, let me show you that how we can perform this algorithm. Till now you would have been clear that how we are proceeding ahead with each and everything. Means first a naive approach was there. Let me show you once more so that it is much more clear. So the thing is that first there was this naive approach where we were just going from the begin word going till the end word and were comparing all the paths, and we don't want this sort of thing, right? So that's why we moved towards this approach where we started making a graph, and this graph is required to be directed and acyclic. That we need to keep in mind, and how we are required to make that graph as directed and acyclic. So for that fact we were discussing these things, that there shouldn't be any edge between the same layer nodes, and there we are also required to maintain a visited data structure in which we will keep the visited nodes, and that's the thing. And now comes the part that how this algorithm will work, which we were discussing till now. So here first we are required to store the words in a word list in an unordered set. This is the only thing which we are doing so that word could be easily removed during the BFS. This is the thing which we are doing, as we need to remove all the words from the previous layer. And why we are required to remove all the words from the previous layer? Because one thing is there, that we are maintaining a visitor node also, and the second thing is also there, that we are removing from the previous layer so that we don't go towards upward direction in the search of finding just one difference of the word and lengthening our path. Basically this is just reducing our path length. So that's why we are required to do this. And then we are required to perform BFS, and while performing BFS we will be able to figure out a shortest path. And how we will be able to figure out? First thing in that is that we will be adding edges to our adjacency list. We are here forming our graph. While performing BFS only we will form our graph in our graph would be formed in such a manner that it will produce the shortest length only. And how it will be doing so, that I'll discuss now. That once a level is finished, remove the listed words from the word list. So the thing is that while we would be making our graph through the BFS, then once the level is finished, then we'll remove the listed words from the list. That would be also then in the first, we were removing our word from the unordered set, so that from the layer 1, all the words have been removed. But those words would have been in listed list also, because we are performing BFS. So we are required to keep those words somewhere so that we could perform BFS on the same. So that's why here once a level is being finished, we'll also remove those listed words also after those words have been processed with the creation of those edges between other nodes. So that is the scenario here. And then start from the begin word. Now till now our graph had been made because of BFS. So that's why we'll start from the begin word, and while keeping track of the current path, here what we are doing is here we are showing all the paths. So that's why, and these paths are basically those paths only which are starting from the begin word and ending at the end word. We are now figuring out with those paths only, not those paths which never end to the end word. So start from the begin word, and while keeping track of the current path, as the current path traverse all possible paths, whenever the path leads to end word basically, show the path in the shortest path. So this is a thing which we would be doing during our backtracking step. So to be precise, what we are doing is that we would be having all our nodes with us, which we'll get from our word list, and those word lists we'll store in an unordered set. Now unordered set so that we could easily look up into the same and also erase from the same. And then we need to make neighbors and store them. So after that we will be making our neighbors. Why we are making neighbors? So that we can complete the criteria of difference between two adjacent words should be just one character. So for that criteria only we are just making this thing. And then what we would be doing is that we'll pass above form neighbors into our BFS function where edges would be formed. So till now our graph would be completed, and now we are required to traverse into our graph. So that's why now backtracking is required to find all the paths, and those paths would be by default shortest only. So this is in precise which we would be doing in our algorithm in our coding part. So now let me explain you more into depth about the function which we would be making, so that it would be more clear to you and you could code yourself also. So now let us first take one example. Say our begin word is red, right? So now how we would be forming our neighbors is that in this word red we will be changing just one character, right? And how we can check that we are changing one character, and after that is it there in our word list or not? So we'll first do that first character, that is R, then we'll change first character R to A, then to B, but all other characters are same as it is, and like this we'll change till ZED, right? And now in all these characters we'll also keep a check that does that particular word really exist in our word list. If that particular word exists in our word list, then in that scenario what we would be doing is we'll simply store that word into our neighbors vector, and then we'll directly move ahead in our loop, and then we will be checking for a second character in our red word. Then when we transform our RED to RAD, then RBD, RCD, and so on till RZD. So in all these also again we will be checking that is there any character ID means after transformation of any character, is there any word which was there in our word list? If that was so, then we will directly store that into our neighbors vector. If that was not the criteria, then what we will be doing is we'll then directly store back that particular word to this red, and then we'll go to next step, that now we are required to check for our third character. Means the thing is that there are 2 conditions. First condition is that we will pick up one character, and we'll transform that particular character from A to Z, and we'll check that if that particular word is present in our word list or not. If it is present, then we'll directly push that to our neighbor, and if that is not present, then we'll directly transform our present word to the red word again. That is the thing which we will be doing here. And then after transforming it to red again, we'll check for our next character transformation. So this is how we will be checking for all the characters in a particular given word, and this was all what our neighbor function will be performing. So now comes the next part, that this was only about figuring out that which all nodes could be our neighbor. But now this was not all which is required. We also required to form a graph out of this, so that at the end we could figure out that what all paths should be there, which will be our answer. So that's why now the thing is that we are required to do BFS for creating our graph. I always used to think that BFS is the thing which is just used for traversing in a particular graph. But after this question, I came to know that, yeah, BFS is something which we can also use to not just traverse into a graph, but also to form a graph. So here the thing would be that it has the neighbor string from this particular neighbor function. And this particular neighbor string, it will be now passed to this particular function. So we will perform BFS on the word list, and we will mark that particular word as visited, and we'll form an adjacency list. And in this adjacency list, these neighbor strings will come into picture. And then what we will be doing is, for performing this BFS, we will be pushing all those words into the queue for getting its next turn. That is the scenario, because we are required to do BFS on each word. So that's why we are required to push that into a queue. This is the basic functionality of doing BFS. And then at the end, we are required to remove word of previous layer. That's the thing which we would be doing here, because of the visited data structure, and thus making it a acyclic DAG. Basically making it a DAG, acyclic directed graph. So after performing this BFS function, we will be able to get with our acyclic directed graph. That is the scenario here. So basically this would be the graph which will be created here, is this thing. After performing BFS, we will be able to create this graph. So that's what we are doing here. Now comes the part for backtracking, that after our graph is now being constructed, so now comes the part that how we are required to figure out with our paths, right? So for that purpose, we are required to do backtracking. Now here comes one more interesting part. The thing is, rather than figuring out and rather than even making a graph from our source node to our destination node, I will be performing this, forming this graph from our destination node to our source node, so that we are easily able to figure out with path, because even if we form a graph from source to destination, then in some step we would be required to reverse it, and in that reversal it will take us more time. So that's why it is much more preferable that we form a graph which is from end node to source node. So what I would be doing here is that here I would be going ahead with this particular task which is being given to us. Here you can see directly that this particular, okay, 1 minute. So here you can directly see that this red, TED, REX, text, TAD and TAG. So here red is the starting word and tags is the ending word, right? So what I would be doing is, I'll form the graph not from this particular red to tags, but I will be forming the graph from tags to red. Basically a reverse graph I will be forming, and then after forming that graph, I will be performing backtracking on the same. And how I will be performing is, I'll check that what all nodes are being connected with my this particular tag, and then I will check that does it connect to my this source word also or not. So I'll go to this tags, then I go to tat, then tid, and then red. I figure out that now I have reached my source and destination are now equal, right? Means my present node and the source node, destination node are equal. Then I'll simply store this particular path into my shortest path, and then I'll simply pop out this particular node, and then I'll move to this particular parent. And now I'll check that are there any other paths which are there, and then for that scenario, yeah, there are no other paths, so I'll directly backtrack to this tab, and then again I'll check that are there any other paths. So no, there are not. So then again I'll backtrack to tags. So now tags will check that yes, it has one more path, so it will move here, and then it will move to TED, and then it reaches to this destination, that is red. So like this only, then again it will pop out, and then it moves back to parent, then pop out, then move back to parent, and then pop out, then again move back to parent, and then tags again check that is there any node left, that yes, Rex is being left, then it will go to this red again. And that is the scenario how we will be doing this backtracking operation, and this is how all three functions would be there. So now this was the overview that how we are required to perform this algorithm and how the functions would be working in the same. But yeah, before moving ahead for the coding part, let me also explain you about the time complexity so that you are clear in your mind that how it really works. So now here comes the part about the time complexity in the space complexity. So here you can see the time complexity is basically n into k square plus alpha. So here n simply represents the number of words in the word list which is being given to us, and k represents the maximum length of each word. And alpha is basically the number of possible paths from begin word to end word in the directed graph. Because there are a lot of paths which are being there, but we are required to just choose for that one path which is leading us to end path. But still, the thing is that while we are forming our graph, we will be somehow keeping a check that does it really reach our end word or not. Although this operation would be now minimized just because of our BFS only. So that's why I've also included this into a time complexity. So the time complexity is basically this one. So for BFS, this is n square. For finding neighbors through find neighbor function, it is basically order of k square, and that is because of the length being involved. So that's why it is k square. I'll show you the function. So there you can see that how it is k square. And then as we are doing for n words, so that's why it becomes n into k square. So this is the overall time complexity for this particular function. And now comes the part for the space complexity. So the space complexity is basically n into k for storing in our set which we were using. As I already told you that we are copying all the words from the word list into our unordered set for easily lookup and even erasing all the words from there. So for that purpose, our space complexity is n into k. And then as we would be doing that, backtracking, so their stack would be involved. So for that total n words would be there which are being involved. So that's why here also a recursive stack space complexity is also order of n. And then about the adjacency list which we are forming, because we are also forming our graph here, right? So there would be max n words being stored into our adjacency list, and that's why space complexity from this is also n. So the overall space complexity is order of n into k. So that is the scenario here. So this was overall explanation of this particular algorithm with the whole time complexity. And if you ever feel that you are like unable to check out that how all this is being performed, you can rewind the video a bit and you can take the explanation again. But yeah, if you have some more doubts, then you can comment that down also. So now comes the part about our code walkthrough. So let me now give you a code walkthrough for this particular question. I've also commented so that it becomes easy for you to understand. So now let us first start from our main function which is being there. So now the thing is that we are given with unordered set, not given, but we are by own self creating. The thing which I was saying that we are copying all our words to this unordered set. so that we could efficiently delete it when we would be performing BFS. Then we are building a DAG using BFS. So this is the thing. We would be calling our BFS function, and in that we will be passing our begin word and end word and our copied word list, basically this one. And then after performing the BFS, we will be having this current path where we have already inserted our end word into the same, so that every path will start from the end word. And why we are doing so? So that we are easily able to check from our end word towards our source word. The thing I was saying, that rather than forming the graph from the source word to destination word, we are forming our graph from the destination word to source word. So that is the thing which I am doing here. Now comes the next part, that how we are required to do backtracking. So traverse the DAG to find all the paths between end word and the begin word. So this is the thing how we will be doing backtracking, by passing our end word as the first parameter and begin word as the second parameter, and then we will be performing so. And at the end we are required to return all the shortest paths. Now let me explain you how these functions are working. So let me first explain you about the BFS. So here comes the part for BFS which is being there, but before BFS, because in BFS we require that neighbors vector also, then only we can perform BFS on the same. So that's why let me first explain you this neighbors which is there, and you can clearly see I've made all these extra functions into our private global scope only. And here you can see I have taken adjacency list as unordered map, where the first part of the pair is string and the second one is vector of string. And this is because our string would be our current word and vector of string would be all other words which are being there. It will be stored corresponding to that. And then we are taking vector string which will be storing our current path, and vector string which will be storing all the shortest paths which are there. Now comes and this is the only thing which we are required to return also. So now here in this particular neighbors function, what we are doing is, here we would be returning this vector of string, and we are taking word and unordered set word list. Why we are taking so is, we will be taking words so that we can compare that by modifying each character, the thing which I was saying earlier for that red example only, that for each character we will be checking, by after modifying each character we'll check that does that particular really exist in this particular unordered set or not. That's the thing which we will be doing here. And then in this vector string neighbors, we will be pushing all those if we are able to figure out that it is present in this. Now we are running a loop till this particular word size, and then we will be first storing this so that at the end we can revert back to this particular position. Now we are going ahead by changing each character one by one with A to Z. So first we are checking for ith character, that is I equals to 0. So word of 0 will change with the C. C is first A, right? So from A to Z we will be changing one by one, and first we are checking that if C is equals to old cat, means if it is the previous character itself, or if it is not present in the word list, then we'll continue. That is, we'll now check for the other character, and if that was not the criteria, then we'll directly push that particular word into our neighbor vector. That is the thing which we will be doing here. And after that, when we are able to figure out in this particular, means when at the end we are able to figure out, right? 1 minute. When we are able to figure out, means all these are now being counted, then we will directly again revert back to our older one, and then we'll again start the loop. And then at the end, after this loop ends, we'll return our neighbor vector. So this is all what we are doing in this particular neighbor function. Now comes the part for our BFS. In BFS, how we are constructing the graph is, we are taking the queue, which is but obvious thing only that if we are performing BFS, then we require a queue. But in queue, we are taking the string, so that we are storing all the words only. And now at the starting, we are pushing this begin word, this because we want to start from this particular begin word. But now there are tricks in this particular graph. Remove the root word which is in the first layer, so that we will be doing in this particular, that we will check that in a word list dot count. Basically, if this begin word is there, and will directly erase this particular from our unordered set. That is the thing which we are doing here. Then we are taking one more unordered map, which is basically there for keeping us updated with the visited one. This is acting as a visited one, that this particular string is there, is enqueued, this is there, so that now we can keep a check that do we need to push into our queue or not. If it is equals to 1, that simply means that this is already in the queue and we don't need to push into our queue. So for that thing only we are keeping this, and this is acting as our visited node. So now here we are performing our BFS. So for this particular, what we are doing is, means in this whole, what we are doing is that first we are keeping this vector string visited. This is for keeping the track for our current layer, and this particular was for the whole BFS. Basically here we are maintaining our two sets. One is for our current layer only and one is for our overall performance. So that is the thing. This is also acting as visited only and this is also acting as visited. But this is for our current layer only, and it will it will update itself time and again when we again come here. Now comes the part that for this present layer, how we are going to do is that for this present layer we'll store our first words which would be there in our queue into this current word, and then we'll pop. Because why we will be popping that? Because now we know that we have now kept this particular word into this particular string, so now we can do processing, and so that there is like no repetition again and again, so we are popping this. Basically this is the basic thing for our BFS which we are doing here. And now here comes the part, this vector string neighbors, right? So how it will be getting it is from this find neighbors function which was above. So we'll get neighbors from there, and then for auto word in neighbors, so now whichever word we had directly put means our current word, that is say now red is there because we are beginning from that. So we'll check all the neighbors of that particular word which we will be able to figure out. And in an example for red we were having Ted, and there were 3 words basically there. For a red we were having here Ted, and one more was there. Let me show you that word itself. 1 minute. So in that neighbors part, what would be there? This red which was there, it will be connected to Ted and Rex. That is the thing which we are going to do here. So that's why we are moving with the same. So for auto word in neighbors, so now we are connecting our red with Ted and Rex. Rex was there. Yeah, I guess. Only X was changed and here only T was changed. So now what we are doing, we are pushing are these words, means Ted. First we'll push this Ted into our visited, and then we will create adjacency list. How it would be created, that our word, current word, that is this particular word, that is Ted. It will be directed towards our current word, that is red. Means basically a graph now would be created like this. That is the thing which we are forming here. So basically what we are doing is it stores the children of the present node, and how means the present node which is there is red, and we will be here our Ted basically becomes the Ted is basically here because we are reversing it, right? Earlier the red was the parent and Ted was its children, but now Ted has become the parent and its children is red. And even same goes for Rex. Rex is now the parent and children is red. So that's the thing which we are doing here. Now comes the part if not enqueued, because earlier Ted and Rex were not there in our enqueued part, right? So it will come to this particular, and now we will push this Ted also into our queue so that BFS would be performing this also, and we'll push this Rex also in this queue so that BFS could be performed on this Rex also, and then we will mark both of them as 1, that now we are globally already visited them, so we are not required to visit them again. So that is the thing which we will be doing here. Yeah. So now comes the part. Let me show you that this particular part is now done. Means when both of them, because only these things were there in our queue, so that's why now this thing is done. Now comes the next part, because till now queue won't be empty. Now 2 new words had been added, right? So still this particular loop will run, and now again this visited will be initialized, and enqueued will remain the same only because enqueued was outside itself, right? So that's why it won't be initialized again. It will be storing all the words which are visited. So now comes the, after this particular loop, here is one more loop which we are running inside this, because see, you can see particular hole is being included in the same, and this is for the BFS, for means this is for this, right? So now come about this particular for loop. In this particular for loop, what we are doing is, here we are removing our words from the previous layer. Means basically till now we are able to figure out for our first layer, right? Till now we were able to figure out for the first layer, so now we are required to remove those words from our first layer, so that's why we are performing here. So now here we would be having our visited vector which is being there, so that's why from that we'll check each of the word in our word list, right? And we'll able to figure out that is it there or not. If it is found, then we'll directly erase that from our word list. Basically an unordered map, unordered set which we had taken, means this particular set. So now we are using that set only here, so that we could remove from this particular, and thus we won't be able to figure out again that here one neighbor is there for that particular. So that's why we are doing all this. So this is a scenario which will repeat itself again and again until we are able to figure out with the whole adjacency list of all the neighbors with all the edges being connected through this BFS. And this is the whole logic which we are performing here. So till now we will be able to figure out and form our graph, but now comes the part, the main part of figuring out that what all paths are there which are being connected from our source node to our end node. So that thing we will be performing in this. I already told that till now the graph would have been formed in reverse manner, right? So that's why here we are performing our DFS, basically DFS, backtracking, whatever you want to say, that is the thing which we are performing here. A recursive calls, you can say, because here we are just using them, calling the function again and again, means recursive stacks we are using here. So here this is the first part and this is the base case. So here what we are doing is we are just traversing an adjacency list based on the current source node which is there, and then how we are doing that is, oh 1 minute, had I need explanation for the thing, else I'll explain you here only. Okay, let me show you. I guess I have already made. So here, yeah, I guess this is the one which I was saying about. So let me explain you how I can explain that, what I'm thinking. So here, 1 minute. Yeah, I guess, yeah, now you are able to see the whole function also. This is that backtracking function. 1 minute. This is that backtracking function, and this is what I was saying. So here the thing is that we are having the source and destination, right, in our backtrack. So here we are first passing with the end word, and then we are passing with the begin word. So this is what we are taking, means our source is here end word and destination is our begin word. So what we would be doing is, this is our base case. So we will directly start from this adjacency source of dot size. So how we are going to go ahead with the same is that in our adjacency list, will check for this particular task which is at the first, right? So we'll check till the size of the same. So we'll push the first word we encounter, which we'll encounter is tad. We'll push that to our current path, and then we'll call our backtracking function. So while we call our backtracking function, right? So this backtracking function is now called with, earlier it was the text word, right? But now the word would be this particular tag, which would be there. So then it will again go to this particular loop. Now it will check. Now tag adjacency list will check that what all nodes it is connected with. So it will now go to this TED. So it will push back to our current path with this TED word, and then again this particular backtrack will call with the TED as the string and the TED as the string, and the destination would be this red itself. That would be the thing. And now next again it will go ahead in this particular loop, and then it will check for the TED, and TED will check for what all node it is connected. So it will say that now it is connected to red itself. So now red and the red would be passed. So here source and destination, both of them are red. Now it will treat this particular base case. That source, that is this red. Destination, that is this red. Both are same. So now it will be pushed back to this particular shortest path. And how it would be pushed back is by reversing it here itself. That is the thing. Because we were doing all this in reverse order, right? So that's why while reversing it, it will be pushed here. And after that, because now this particular call is now completed, so now it's time for the backtrack part. So that's why now current part dot pop back, so that it would be pop back from here, and then the remaining call which was there for the loop for this TED, that will proceed. So now we can say that TED don't have any other node, so that's why nothing would be pushed here and nothing would be done for this backtracking, and then again this would be pop back. So TED would be pop back. So now it control comes to TAD, and now TAD will check for all other things, and then again there would be the same scenario. So TAD would be pop back, and then it comes to the task. Now task is having a loop remaining to go ahead, so it will check for text. So now this source would be that only, and then I would be 1, and it will be consisting of this text, and that will be pushed to this current path. So like this only the whole process would go on, and this code will work in that manner. So this was all for this backtracking also. So now I have completed for the explanation of all the functions which I have used here, and you could find this code in the description itself. I'll copy paste the whole code there. So this was all for this particular question. If you have any doubt, you could comment that down. I'll try to resolve that. So this was all. I know it is pretty much long video, but I know when we are required to explain the whole thing that it takes a lot of time. So yeah, thanks for watching.